Okay, let's restart. Yeah, and yeah, decreasing thickness of stationary plate leads to decreased plate height and decreased um, retention time, also decreased capacity for analyte. Okay, you will see in detail. Yeah, here. Okay, let's first consider the effect of open tubular column inner diameter on resolution. Okay, and we will compare these two chromatograms. Okay, the first one here, the inner diameter is 0.32 millimeter, and this one is 0.25 millimeter. Which chromatogram is better, right? Definitely this one. Yeah? This chromatogram is better, right? Because look at that. This peak 1 and 2, right, is more well separated, yeah, for this column, yeah, when diameter is reduced. Okay, and but you see this separation time here on the right, on the left column, is less than 2 minutes. Yeah, separation is done, but this one is separation requires a little longer time. Okay, yeah, and so narrow column provides a high resolution here. This one, okay, narrow column provides higher resolution, but requiring high operating pressure and lesser sample capacity. Okay, the high operating pressure. Why? Since the column diameter is small, and then you need more pressure to push your carrier gas through the column. Okay, and less sample capacity because the volume inside the column is small. Okay, but uh, it gives you high resolution. Why? Since the column diameter small, and then all the analytes inside the column now the diffuse into the central page very more rapidly than uh, the for the column of larger diameter. Okay, so here resolution is proportional to actually what, which one, yeah, resolution is proportional to the length, okay, of the column, and length uh, is proportional to the number of plates. So resolution is proportional to the square root of this one. Okay, number of plates. Yeah, this is already we know the relationship. Yeah, in previous chapter. Yeah? And resolution also can be expressed by this equation: square root of n divided by 4 and multiplied by gamma minus 1. Here, what is gamma? Gamma, n is plate number, and gamma is un, unadjusted relative retention. Okay, unadjusted relative retention. Yeah? Unadjusted means that you start from your injection time. Yeah, the set injection time to 0. Okay, and then you measure the retention time. Yeah, that is the and then we compare, yeah, the retention times, which is what gamma means. Okay, and this one actually has been done with wall coated open tubular column at 95 degrees C. Okay, and this is column residential phase. You see, the the kind of code, and the inner diameter is 0.25 millimeter, and carrier gas was in the helium. Okay, so this resolution increases in proportional to the square root of L. Okay, the column length here. Yeah, let's check this one. Yeah, the RS is proportional to square root of n, and since n is proportional to L, actually, so resolution is proportional to the square root of column length. Okay, yeah, let's take a look at these three chromatograms, but only the difference is the column length. Everything else is the same. Yeah? This one, the first one, was done with 50 meter columns, and second one is column length is 30 meters, and this one is 60 meters. Okay, now this one column length increased twice and then also twice. Okay, and then since the column length is increased twice, two times, and then resolution, what resolution we expect, yeah, will be improved by what percent? Square root of 2, right? So it is 1.4, about 40 times increase, right, in resolution. I recommend you to let me see, calculate the resolution, yeah, by blowing up this one, okay, this chromatograms, and then here, when you increase the column to 60 meters, and from comparing to the first one, and then column length increment is 4, so you expect resolution increased by 2, by the factor of 2, because square root of 4 is 2. Okay, yeah, so you see, definitely you have really good resolution. Okay, but since you increase the column length, and then this separation time also increases here with 50 meter column, and this number 4, it takes about 1.9 minutes. Okay, and this one, when you increase twice, and then this one, this is the last peak. The peak appears at 3.6 minutes, yeah, exactly twice. Okay, so the separation time is proportional to column length. Okay, what about the for the 60 meter column? Right here is takes about 7 point, let me see, 3 5 minutes. Yeah, this is twice of this one. Yeah, and 4 times longer than the first one. Okay, in this case, the helium was used as a carrier gas. Okay, so linear velocity, yeah, not volume velocity. Yeah, linear velocity was 34 centimeter per second. Okay, and let's consider the effect of stationary phase thickness on open tubular column. Okay, at constant linear velocity, let's say increasing the thickness of stationary phase, yeah, that means you make a thicker, the stationary phase inside the open column, right? And then what will happen? Yeah, think about that. What about the separation time? Yeah? If the liquid stationary phase is thick, or maybe not only liquid but also solid stationary phase becomes thick, and then there will be more time for the analytes to be equilibrated inside the film. Okay, because it is thick. So the separation time will be increasing. Okay, and what about the resolution? Yeah? Since more uh, the amount of liquid phase is there, and then resolution becomes higher. If you are not sure, think this way, and then think, what if the liquid phase, stationary phase is really really thin, okay, and then it becomes nothing, right? And then no separation will be done, okay, with no stationary phase, yeah. That indicates that if you increase the thickness of stationary phase, and then resolution also will be increased. Okay, yeah, that is true. Yeah, look at these two chromatograms here. This one is the thickness of a stationary phase is only 0.25 micrometers, and this one is 1 micrometer. Yeah, 4 times thick. Okay, and then these compounds are well separated with a thick film. Okay? Yeah. So increasing thickness of stationary phase increases retention time. As I said, it increases the retention time, but retention time and sample capacity, okay, and increases the resolution. Yeah, this is important. Okay, here. Uh, of all eluting peaks with capacity factor, this one is k prime is less than 5. Anyway, increasing the stationary phase thickness gives you advantage of what good good separation or good resolution. Okay, a good separation, but separation time you may suffer. It will increase. So thick film of stationary phase can shield only light from the silica surface, okay, and reduce tailing, but can also increase bleed. There is a bleed, decomposition and evaporation of a stationary phase, okay, at elevated temperature. Normally, 0.25 micrometer thickness is standard, but thicker film are used for volatile lights. Okay, here. Yeah. Look at that. Here, uh, yeah, increasing uh, the thickness of stationary phase reduce the tailing. Okay, tailing means this one. Okay, this peaks uh, doesn't drop rapidly, but it has it slowly drops. Right, this is a tailing. This one is also tailing. Yeah, but and then with the thicker film, the tailing becomes small. Okay, here also this is also tailing, but look at this thickness. Yeah? This is much thinner. Okay, well separated. Okay? But bleeding, it may increase bleeding. Okay, bleeding is the decomposition and evaporation of the stationary phase. Okay, let's take a look at uh, the bleeding first. Okay, where is the bleeding? Maybe, yeah. Uh, let's consider this one, column bleeding first. Bleeding is the decomposition of stationary phase, giving decomposition products from the column. Okay, see, let's assume, let's imagine that you coated the the inside the column, yeah, very thick. Okay, okay, and then what? There are many stationary phase inside the column, and then sometimes at elevated temperature, and then when you run the gas chromatograph, and then you may mm, there is a more chance for the stationary phase to decompose, okay, and may some of it may come out of the column. Okay, that's the bleeding. Yeah? So this uh, this bleeding results in elevated background signal. Okay, which means that here usually this background signal, this one. Okay, this is there is no actually background signal. Background signal is there, but it's constant. Okay, so you want to maintain this background signal as small as possible. Yeah, but with bleeding, this background signal may not be constant, but may increase. Okay, RLAN stationary phase here. Now, this is ordinary stationary phase. Look at uh, this structure of this one. This diphenyl dimethyl. Okay, diphenyl and dimethyl polysiloxane. Now, this is a very favorite stationary phase for open tubular column. This may bleed if you coat too much of this one onto the inner wall of the column. So, but this one, Arilan polysiloxane, this one uh, gives increased thermal stability, so bleed less at high temperature and are especially suitable for GC mass. Okay, this one. To reduce interference from column bleeding, use the thinnest possible stationary phase and the narrowest and the shortest column. That provides adequate separation. Okay, yeah, there is a way to reduce bleeding. Okay, which is that you use the thinnest column stationary phase and narrowest and shortest column. Okay? And O2 oxygen is a main source of bleed by oxidizing the stationary phase. So when the oxygen is enters the column, and then it may react with the stationary phase. Oxygen is a very active chemical. Okay, so you have to block the oxygen enter. Okay, high purity carrier gases should be used. Okay, so when you use, for example, helium gas, and then first you pass the helium gas through the oxygen trap. Yeah, otherwise maybe little amount, yeah, of oxygen may be in the carrier gas. Okay? To a lesser extent, this water can break down the stationary phase by hydrolysis, and also not only oxygen, but also there will be a small amount of water in the carrier gas. Okay? And this water effect is not as great as the oxygen, but you have to avoid this water. Okay? Because water, when it enters the column, it may cause hydrolysis. Okay? This is column bleeding, so be careful. Okay, let's temporarily stop here.